Okay, so here are two additional related rate problems. So we have a hot air balloon, which is 150 feet above the ground. When a motorcycle passes directly beneath it, traveling in a straight line on a horizontal road, going 40 miles per hour, which is 58.67 feet per second. If the balloon is rising vertically at a rate of 10 feet per second, what is the rate of change of the distance between the motorcycle and the balloon 10 seconds later? Okay, so let's see what we can draw here. So you've got this horizontal ground. You've got a balloon right here. And there's the motorcycle. Okay, now what will be happening in 10 seconds? The balloon will have risen and the motorcycle will be over here somewhere. Now, this distance from here to directly under the balloon we'll call x. And we can calculate x because the distance is the velocity times the time. And the motorcycle is traveling at 58.677 feet per second. And it does that for 10 seconds. So that's 587 feet. So x, that's x. And we can do the same thing for y, because the balloon is rising at a rate of 10 feet per second. So this distance here, we'll call that y. We're going to call this distance y, which is the total distance. So remember, this here is 150 feet. So the question is, how far does it travel here? And that, I'll call it delta y. And that's going to be the velocity in the y direction times time. So we go over here, the balloon is rising vertically at a rate of 10 feet per second. And the time is 10 seconds, so that's 100 feet. So y is 150 feet plus 100 feet, which means it's 250 feet when they want us to do this calculation. And we can draw a right triangle here from up straight from the motorcycle to the balloon down to the road, and horizontally along the road. So what you've got is a right triangle where one side is y, one side is x. This is, we'll call S. So there's two things we need to do. Well, first thing we need to do is, what is dx dt? Well, that's the rate of change in x, which is the speed of the motorcycle. So that's 58.67 feet per second. And dy dt is 10 feet per second. That's the speed it's rising. So we have dx dt, we have dy dt, we have x and y. What we're trying to do is calculate what ds dt is. What is the rate of change of this distance? So that's the question mark. The only thing we're going to need is S. So it's the hypotenuse of our triangle. So use the Pythagorean theorem, solved for the hypotenuse. And X is 587 feet. And Y is 250 feet. So we're getting some number bigger than 587. 587 squared plus 250 squared, and take the square root of that. So I get 407,000. Take the square root of that, you get S is 638 feet. Now the equation for the rate of change is the Pythagorean theorem. In this case, x and y and s are all changing, but at any instant in time they're related by this equation. X squared plus y squared equals s squared. So that's our geometric relation. You take the derivative of every term with respect to t, and because they're all not t, they're x, y, and s, and none of them are constant, we're not going to get 0, so we're going to have terms involving every one of these. So you take the derivative of x squared, which is 2x, and then add your x prime, or dx dt. Then you're going to have 2y dy dt, and on the right hand side is 2s ds dt. So you can see these 2's are going to cancel out because we have one in each term. And then we're going to solve for ds dt because that's what they're asking for. So to do that, we divide everything by s. So we'll get x over s dx dt. So it's x divided by s dx dt plus y over s dy dt. And there we go. Okay, so that is the related rates, and you can see that I've got all this stuff here. I've got all the pieces to the puzzle. I just need to plug them in. So the rate of change of the hypotenuse with respect to time is x, which is 587 feet, divided by s, which is 638 feet, times dx dt, which is 58.67 feet per second. Y is 250 feet divided by 638 feet. So that's y over s times dy dt, which is 10 feet per second. And we should get some number between 10 and 58.67, I believe. So 587 divided by 638 times 58.67 plus 250 divided by 638 times 10, and I get 57.9 feet per second. So that's the answer. So again, if you think about what we did here, is we created this right triangle with the two sides changing, x and y, and the hypotenuse changing, s. We use the known x and y to figure out s, and then we use the Pythagorean equation as the thing linking all of those, taking the derivative with respect to time using implicit differentiation. We got the relation. We solved for what we didn't know, what we were trying to find, which is the rate of change of the distance between the motorcycle and the balloon, which is this distance, s. Okay, so that's that one. The next one says we have a conical tank with an upper radius of 4 meters and a height of 5 meters. So that's this one right here. Drains into a cylindrical tank with a radius of 4 meters and a height of 5 meters. If the water level in the conic water tank drops at a rate of 0.5 meters per minute, so that's the height here, 0.5 meters per minute, at what rate does the water level in the cylindrical tank rise when the water level in the conical tank is 3 meters and then 1 meter? So let's kind of draw a picture here, two-dimensional picture, just to relate things. So we got this conical tank, and what we know is that the radius here is 4 meters when you go the entire height of the cone, which is 5 meters. Got some liquid in here that's, this distance is 3 meters initially. Now what's the geometric relationship for a right circular cone? The volume is equal to 1/3 pi r squared h. So we had a problem like this before. We have had two problems like this before. And we need to have some relationship between r and h to be able to put this in terms of one variable. And because they're asking us for, or they're telling us what the rate that the tank drops, which is the water level, is the height. So this is h, This is R. R is the distance from here to there. That's the R at that particular height. What you can see is because of this linear relationship between radius and height, the relationship is going to be that the height, actually this height is going to be equal to either 4/5 or 5/4. And because the height is greater than the radius, it's going to be 5/4 R. And you can kind of check it out by plugging in the value. So when R equals 0, H should be 0 too, because it goes to this point. And then at the top, when R equals 4, H has to be 5. So 4 times 5/4 is 5. So that proves that it's correct. And as a consequence, we can rewrite this expression. 1/3 pi for R, we'll put in 5/4 R H. Wait a second, what are we doing? Trying to put this in terms of H. Yeah, so actually I want to do it this way. Trying to do it in terms of H. So it's R is 4/5 H. So you get 4/5 H, that's R, square it, times H. So if you square 4, you'll get 16. So you get 16 pi divided by 3 times 5 squared, which is 75 H cubed. So that's my geometric relationship. And then we can take the derivative with respect to time, so we get dv dt is equal to 16 pi over 75 times the derivative of h cubed, which is 3h squared, but because this is h and the variable we're taking the derivative with respect to is t, you get dh dt. And it says dh dt is 0.5 meters per minute, but it actually is negative because the height is getting smaller, so it's negative 0.5 meters per minute. And h, we already know what that is. H is 3, right? Water in the conical tank is 3 meters. So that's h. So from that we can calculate dv, and let's put a subscript here, v of the cone. So I'm going to put an O here for cone instead of a C, because we've got a cone and a cylinder and they both start with C, so that doesn't help. Okay, so we get dv0 dt is equal to 16 pi divided by 75 times 3 times negative 0.5 meters per minute. So that's 3, and you got to square that, 3h squared times dh dt, which is, oh, I've got those the wrong way around. This is not, that's h. H is 3 meters. Okay, so you got 3 times 3 squared, and then you have negative 0.5 meters per minute. And so what we're going to get is cubic meters per minute, because you got meters squared times meters. So it's cubic meters per minute, which is rate of change of volume per unit time. And I'm just going to do this as a decimal point. So we get 16 times pi divided by 75 times 3 cubed. 3 cubed is 27 times 0.5 with a negative sign, and you get negative 9.0 cubic meters per minute. So this thing's emptying out at this rate. Now what's going out of the cone has to go into the cylinder. So the cylinder rate of change of volume there is plus 9.0 meters cubed per minute. So that's going to be the input to the next part of the problem. So now let's look at the cylinder. So a cylinder's pretty straightforward. So here's a cylinder, and it's got some height, but it doesn't really matter what the height is because there's no relationship between radius and height. So this is going to be the radius, which stays fixed for the cylinder, and the radius was 4 meters. So that quantity's fixed. Here's the height. Okay, doesn't tell us what that is, but it doesn't, to find out what we're looking for, we don't need to know what that is. Okay, now the volume of the cylinder is going to be pi r squared times h. And how do I know that? Because, you know, a cylinder consists of a circle, and then that circle area is pushed up in the h direction. So you get this area times the distance. So this is the area of a circle. That's the height of the cylinder. Now r is a constant because it's a cylinder. It's not a cone. So when I take the derivative of both sides, in this case, pi is a constant, r is a constant, h is not a constant, so that's what I'm calculating here, is dH dt. And what I'm looking for is dH dt, because I'm given dV sub L dt. I already calculated that. That's positive 9 cubic meters per minute. So if I solve for that, I'll get 1 over pi r squared times dV sub L dt. So it just divides both sides by pi r squared. And now we can get it. Now the dH dt should be positive because the tank's filling up. So we have 1 over pi times r, which is 4 meters. Squared times 9 meters cubed per minute. So do that, we get 9 divided by pi divided by 16. And I get, oops, something's wrong there. 9 divided by pi divided by 16. And so dH dt is equal to plus 0.18 meters per minute. Okay, I think that's right. And, you know, we'd expect the height of the cylinder to be increasing at a lower rate than the height of the pyramid or the cone is decreasing. Because here you've got this entire radius to add material. Here we're down here at 3 meters height, which is going to be a smaller radius. So there's less surface. This surface area on the top is less. So when you add a certain amount of volume, or subtract a certain amount of volume, it's going to cause a bigger drop in the level. Okay, so that's the answer. Now, the only thing that's going to change if we do the second part, if you look at it, the only place the height of the cone comes into play is here. So what we would do is for 1 meter height, we'd have that squared. And so let's just plug everything else in. So you got 16 times pi divided by 75 times 3 times 1 squared times minus 0.5. And so I get negative 1.0 cubic meters per minute. And the reason is because you can see here 3 squared is 9, 1 squared is 1, so it's a factor of 9, 9 over 1. So this, for the second case of a radius of 1 meter, you're going to get, or a height of 1 meter, you get 1/9 the amount of flow So now that you come over here to this cylinder, and the only thing changes is this, because this becomes positive 1.0 meters per minute for the amount that's going in, and so this one becomes 1.0 meters cubed per minute. And so this is going to be reduced by a factor of 9. So if I divide 0.18 by 9, I'll get, for the second part, 0.02 meters per minute. All these other numbers stay the same. Nothing changes. This is 9. So we get 0.02 meters per minute. Okay, so those are the two extra problems.